All right, let's go ahead and do WebWork7. So this blue line here is the tangent line for our function, and the name of our function is f of x. I guess that works. Okay, so here's f of x. And all right, this blue line, they tell us the equation is y is 3x minus 3. Okay, sweet. So this spot right here of tangency, I guess that happens at x equals 3, and that's what we call a. So this would be a is equal to 3. I was trying to write there on my pen and I can't. Anyway, f of a is the y value, and the important thing is that f of a is the same as the linear approximation at a. So we know what y of a is. If I plug in 3, I have 3 times 3 is 9, minus 3, I get 6. Okay, so that's going to be my second blank. And now if you move away from 3, so whether I move to the right or to the left, and let me make some room here. Okay, so here's 3. If I move over to, say, 3.4, then the value on the blue curve is pretty dang close to the value on the black curve, which means f of 3.4, the value on the black curve, is approximately y of 3.4, which is the value on the blue curve. So I'm just going to plug 3.4 into my equation for y. So y of 3.4 is 3 times 3.4, whatever, minus 6. Okay, so let's just go ahead and enter all of those. And so we have 3, and this was 6, and this is 3 times 3.4 minus 6. All right, is it an over and under approximation? So because the black curve is above the blue curve, I should say, because the blue curve is below the black curve, we are an under approximation. So under, which we might have to do text mode for, which is this button. So let me actually try that again. Hit text mode, under, yes, there we go, great. Let's go ahead and submit. All right, so why don't you like that? So use the linearization to approximate that is 3. Oh, I took away 6. Sorry, I should have taken away 3. I had 6 on the brain. Great, there we go. Right, I'm looking at the y equals 3x minus 3 and plugging in 3.4. Okay, cool. So that's the only problem with the picture. So everything else is the same idea, and maybe I'll sketch some pictures, but that's gone. All right. So we have some mystery function that we don't know, but we know that its derivative at x equals 100 is equal to 3. Oops, sorry. And we also know that when x is 100, f of x is 34. So that means that near x equals 100, f of x is approximately, and then what I'm going to put here is the linear approximation. Okay, it's approximately f of 100, where you start. This is where you start, plus, and then I'm going to put in how much you change, the change in y, which I'm going to think of as slope times the change in x. Okay, we are hopefully, we've seen before that change in y divided by change in x is slope. That's the whole idea. So what am I going to use for slope? This is going to be f prime at the x value, f prime at 100. So I guess I'll just put everything in really quick, times. And what's my change in x? Well, it's whatever my new x value is minus whatever the initial x value is. Okay, so this is the whole idea. So what do we get? So f of 100 is 34, plus, and f prime of 100 is 3, and the new x value is 96.5, and I take away 100. Okay, so this computation here is what goes in the blank. And you could compute it, but why when we can just let WebWork compute it? So I have 34 plus 3 times 96.5 minus 100. There we go, boom, and there it is. All right, so we're just going to do linear approximation over and over and over again. Temperature H in degrees Celsius of a cup of coffee is placed on a counter and is given by H as a function of T. So how hot it is a function of how long it's been sitting on the counter. If the derivative is positive, that means the temperature is increasing as time goes on, but that doesn't make sense. Like, it's not on a stovetop, it's on a counter. So the derivative should be negative. We should have the temperature decrease as time goes on. And so that's me reasoning my answer. Okay. For the following, enter units in text mode. Okay, fine. What are the units of f prime of 15? Okay, so let's address that really quick. So we're measuring in degrees Celsius, which I'm not too sure what they want for degrees. So let's see. Mass, volume, force, work, and energy. Miscellaneous. Sure, degrees Celsius. Deg C. Okay, fine. All right, so here we are. And type deg C, and then divided by min because time is in minutes. Okay, and let's talk about why that's the case. So we have some kind of function, okay, h of t, and h prime, let's just pretend we're looking at this spot here. So h prime of t, but if I were to pretend like this at some spot a, okay, so right here was x is a, okay. Anyway, h prime of a is this slope at x equals a. Okay, slope, that's a change in y divided by a change in x, so to speak. Okay, really I should write change in h divided by change in t. It's the change in the output divided by the change in the input. Okay, so my output, my h, this is degrees Celsius, and my input, this is t, this is measured in minutes. So what I have, when I look at this, if I include units, I have a change in temperature divided by a change in time. I have degrees Celsius divided by minutes, so that's why I have that unit there. Okay, now suppose the absolute value of f prime of 15 is 1.5, and f of 15 is this, fill in the blanks, including where needed, blah, 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 blah. Okay, great. So now they say f prime not 1.5, sorry, f prime of 15 minutes. So at 15 minutes, the rate of change is 1.5 in absolute value, but we know that the derivative is negative because the temperature is decreasing as this cup is sitting on the counter. So they're just trying to make this like ever so slightly harder. The whole idea is that f prime at 15 is negative 1.5, okay? So, all right. They're giving us some blanks that are setting us up for a linear approximation, it looks like. But all right, so at 15 minutes, after the coffee was put on the counter, its derivative, sure, is, I suppose, maybe it wants 1.5 here, I don't know, and will, okay, so never mind, I see. All right, so at 15 minutes, the coffee was put on the counter, its temperature, okay, what is its temperature? It was 65, but the temperature will decrease by about, okay, so now we have to use this approximation. In fact, I'll just tell you what we're doing here, sorry. So there is one little sneaky thing. It says 15 seconds go by, but 15 seconds is a fourth of a minute. It's 15 divided by 60, you'll get a fourth, okay? So that's how much time goes by, and for every minute, we have a certain change in temperature. In fact, the derivative, we have minus 1.5 over 1, and this is deg C over minute. Okay, here I'm using this fact. I'm using the fact derivative at 15 minutes is negative 1.5. And this negative 1.5 suppresses units. But if we include the units, it looks like this. So now, for each minute, the temperature drops by 1.5 degrees Celsius. Okay, well, I didn't do a full minute. What I did was a quarter of a minute. So my new change in temperature is this. It's the change in time times slope, and that'll get you the change in h. I'm looking at this ratio here. The change in h divided by the change in t is slope. So now if I'm going to multiply by the change in t, and I'm going to plug in what my slope is, it's minus 1.5, and then my change in t. So see, my change in temperature is minus 1.5 times my change in time. So I just wrote down my change in time. It's 15 divided by 60. So I should multiply this by negative 1.5. That's my slope. Okay, and I think, yeah, let's go ahead and do that. Unexpected character. Oh, God. Okay. Was I not in text mode? Let's see. Text mode. Deg. Shift C. All right. Let's hit submit. Okay. Okay, let's try this again. All right, what are the units of that? Let's be in text mode. Let's hit this. Let's try that. Let's see how it likes that. I don't know. Okay, great. So if you're having issues with that, hopefully that helps. Okay, now I'm missing units here. That's why they're mad. So let's go back to text mode and enter deg C. That's how hot the coffee is. And how much will the temperature change? This much. Great. So now, okay, you still don't like that. So what's going on? Next 15 seconds. 15 minutes, the temperature, blah, blah. Okay, what don't you like? At least one is not correct. Okay, and we're told this is negative 0.375. So, deg C. All right, for the following, enter units in text mode. Oh, I see. Okay, so right here, how I chose decrease, that means I don't have to include the negative. The decrease makes it negative, right? This is just talking about the total change. So that's what's going on. All right. All right. Use linear approximation, blah, 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 blah. Great. Let's just draw a picture really quick. So the square root function looks like this. Square root of 0 is 0, and it kind of, boom. And importantly, like, it really kind of like, it doesn't fully flatten out, but like it gets less and less steep, right? It sort of flattens out. So anyway, if here's 64, then the tangent line at 64, I put it there. We'll just pretend I put it on this spot here. That's not good. Try this again. That's a better tangent line. We'll pretend I'm looking here. Okay, let's move this to right there. Okay, great. Cool. So the red line and the blue graph are pretty close. And let's figure out the equation for that red line. So the linear approximation of x is f of a plus f prime of a times x minus a. Okay, and a is the nice number. A should always be something nice that you can compute, and x is going to be something that's like a little bit grosser. So in this case, that's going to be the 64.3. Okay, and it's even grosser if I write it because my penmanship is so bad. Okay, so let's plug in all the stuff. But this requires us to do a little bit. So we know that f of x is the square root of x. So f prime of x, well, this requires the power rule. We just need to remember the square root is the 1/2 power. So I have 1/2 x to the, and the power rule says to do that. But 1/2 minus 1, or if I have if I have 50 cents and I owe someone $1, then I have negative 50 cents. Okay. And another way I could write this is 1/2 times 1 over the square root of x. And another way I could write this is 1 over 2 root x. Okay, all of these are saying the same thing. That's the point of the equal sign. Okay, anyway, so, what is f of 64, aka the square root of 64? That is 8. All right, what is f prime of 64? This is 1 over 2 times square root of 64 is 8. So that's 1 over 16. Okay, so I have this information and that information, and I'm going to do the linear approximation. So the linear approximation, this was f of 64, it's 8, plus f prime of 64, that's 1/16. And now x, my x value is 64.3, and my a value is 64. Okay, and this is L of 64.3. Okay, right? I've plugged in x, it's 64.3. Otherwise, those would just be x's. All right, but let's enter all the stuff they want. So what was the slope in this equation? It was 1/16. What is the b value? Okay, fine. So we have to do some algebra here. So let me briefly make this back to an x, not u. If this was an x and this was an x, then you can do some algebra, and we'll have 8 plus 1/16 x minus 64/16. Okay, if I distribute that. And so that's how I got the slope was 1/16. Now, if I combine those two numbers, I'll get the b value. Combining those two numbers is really just, okay, look, I know that 64 divided by 16 is 4, but you could always write 64 divided by 16. It doesn't matter, right? And you can always just let WebWork compute it and say, oh, it's 4. Okay, and so now we have all these numbers here. Anyway, what is my final answer? We're just plugging in x is 64.3. So I have 1/16 times 64.3 plus 4. Great. And now you can use this form, okay, and plug in 64.3, or I used y equals mx plus b form, right? And so I just used the b, which was 4, and the m, which is 1/16, and I just literally plugged everything in the bottom there. Okay, great. That's all we're going to do. Like, this whole thing, it's just equation of the tangent line, which is point slope formula, and then plugging stuff in. Okay. We want to approximate cosine of 6.1 using the tangent line approximation. All right, well, this is approximately cosine of 2 pi, and that is 1, so I already know the answer is going to be 1, but whatever, let's see it happen. So why do I say that? Well, 2 pi is about 6.28 because pi is about 3.14, so we multiply by 2 to get there, right? So, okay, this is the a value that I'm going to use, right? A is the nice thing, right? This is not the a value I'm going to use. That's the approximation, okay? Cosine of 2 pi, I know, it's 1. Cosine of 6.28, this is not 1, it's something gross. All right, anyway. All right, so the point slope formula. If you can remember that y minus y naught over x minus x naught, if you can see this and think, gosh, that looks like slope, you would be correct. That is the slope formula. And then we just move this denominator over. Y minus y naught is equal to m, x minus x naught. Great. And then we do a substitution. See, y is going to be our function at x. So the whole idea is, well, what do I really want to say? I'll do this. Y naught is our function at a, and x naught we're going to call a. So now we have y minus f of a is equal to and also our slope is f prime at a. So it's equal to f prime at a times x minus a. Right? And I understand that, there's this big jump that happens going to math in college versus high school. And it's that the people who are teaching math, like, we're suddenly very fluent in this new language. And so our brains, when we see stuff like this and this, we know that's just a number, okay? And we are just as comfortable working with this form as we are with this form, okay? If you feel comfortable here, okay, but you feel uncomfortable here, it's because there's a disconnect where when you see this collection of symbols, you're not just thinking, oh, that's my slope. That's all that is. That's just my slope. And when you see this collection of symbols, you're not thinking, oh, that's just a y value. That's all that is, okay? At least that's my guess. I can't tell you what you are or not thinking. But okay, so anyway, the formula in the equation sheet just moves this thing over to the other side. So what we're going to have is that the linear approximation is the f value at a plus f prime at a times x minus a. This is the form you have in the equation sheet. This is what we want to use. All right, so this is L of x is equal to cosine at 2 pi. I've talked so long that now I've sort of like lost some perspective. 6.1, that's pretty close to 2 pi. And 2 pi is something nice to plug into cosine. So that's how I know that my a value is 2 pi. Plus, what's the derivative of cosine? It's negative sine. And now I need to plug in 2 pi. Okay, so this whole monster here is this thing, and f of a is this thing, which is this thing. Great. All right, so now I have to do x. X is the 6.1. It's the value that's a little bit grosser, minus 2 pi. All right, and what, oh what, is sine of 2 pi? Well, if you ask your calculator, it'll say 0, and if it doesn't say 0, that means you're in degrees and not radians. You got to change your mode. Okay, so this whole thing goes away. It's just 0, and our approximation is cosine of 2 pi, which is 1, which in the very beginning I said we're going to get 1, but whatever. Okay, so what is f prime of x? It's negative sine of x. Okay, so what's f prime at 2 pi? It's negative sine at 2 pi, but that's just 0. Okay, so I'm just going to say 0. What's the linear approximation? It's 1. That's what we got over here. It's 1 plus 0. It's 1. Okay, so what is this? It's 1. All right, there you go. Cool. All right. Do it again for natural log. All right. Sweet. Okay, so what's the derivative of natural log? It's 1 over x. And what happens when you plug in 1? Well, you have 1 over 1, so that's 1. Okay. What's the formula for the linear approximation? This should be f of 1. Okay, so wait a second. F of 1, that's my natural log. Natural log is f of x, right? I have to plug in 1. So that's ln of 1. What's ln of 1? It's 0. But you could write ln of 1, and it would still work. Okay, I'll show you that it would still work, but whatever. Okay, f prime of 1 goes here, so that's 1. And I have x minus 1. Okay, there you go. And I'll just hit submit really quick. So there it is. You can see it all works. It just hides the fact that this is actually a much easier equation. It's actually 0 plus all that stuff. So let's make it 0 plus all that stuff. And in fact, wait, 1 times something, well, that's just the something to begin with. So this is our linear approximation. It's just x minus 1. That's all it is. Okay, so if I plug in 0.9, I have 0.9 minus 1. That's minus 0.1. And if I have 1.1, well, I do 1.1 minus 1. That's 0.1. Okay. Yes, I know it's equivalent. That was my whole point of that whole... Okay, whatever. Anyway. Oh, I didn't mean to hit submit. Sorry. Next problem. Great. Use linear approximation to approximate blah. All right, fine. So, let's see if... So I want to do f of 1 plus f prime of 1 times, and then 1.02 minus 1. Okay? This is the idea. All right? That's the linear approximation formula. And what is my function? My function is 1 over x. Okay? It says that in essentially the first sentence. So 1 over x, if I plug in 1, I have 1 over 1, but why would you ever write that? Right? This is just 1. Okay? Now, if you take the derivative of 1 over x, okay, maybe that's worth talking about. It's a power rule, but it's a sneaky power rule. Okay, so 1 over x is x to the negative 1 power. No derivatives happened. Okay, this is equals. I haven't done a derivative. If I take a derivative of 1 over x, that is the same thing. This is just algebra. Taking the derivative of x to the minus 1. Okay, now I'm going to take the derivative. Okay, when this symbol is here, I have not taken the derivative yet. But now that symbol is going to go away. I'm going to take the derivative. I do the power rule. Okay, the minus 1 came down, and then I do the old exponent minus 1. And notice there's no more of this symbol. It's gone. Okay, it's just like if I say 2 times 3 is 6, the times 2 has disappeared. What I do not write is that. That's not true. The thing I'm supposed to do, I friggin' do it, and I stop writing it, okay? So we're supposed to take a derivative, you do it, and you stop writing it. Look, many of you will think that whole rant was silly. The number of times that on a test or something like that, I see a student write this, okay? Okay, and you're going to lose points. It's not true. The derivative of that is not equal to the derivative of that. What is true is this. The derivative of 1 over x is minus 1 over x squared. That's what this is saying, right? Because the negative 2 exponent means you drop it down to the bottom and you have an x squared. Okay, whatever. All right. So here's my derivative function. I want to do f prime at 1. If I plug a 1 down here, well, division by 1 is, you're not doing anything. So really, I just have that negative 1. Okay? All right, there we go. Why don't you like that? This should be... Oh, because I'm so sorry. I misread this, right? X is 0.102. So the a value that I want to use is 0.1. Because 1 over 0.1 is 10. That's a one that I can do pretty easily. So this should be a 10. And this is a -1 divided by I'll just write it like this, 0.1 squared. It's going to end up being 100, but like whatever. Okay. That all should have worked. I don't know why it doesn't like it. One sec. Let's see. Nice approximation, 0.02. Oh, right, because I have the wrong... Right, sorry, this is my x value. This is my a value. There we go. Okay, nice. Sweet. Last problem. All right, so if we have cosine, its derivative is minus sine of x. And if we take a derivative again, we'll get... So the derivative of sine is cosine, and the minus sign just comes along for the ride. All right, f prime at 0. Well, look, you could write minus sine at 0. You'll get full credit, but sine of 0 is 0. So, boom. F double prime at 0. Cosine of 0 is 1, so we get -1. Okay, I'm just plugging 0 in here. Okay, so what's the quadratic approximation? Let's write down that formula really quick. Blah, 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 blah. All right, so f of x, or he calls it q of x in the equation sheet, it's approximately f of a plus f prime of a times x minus a plus f double prime of a divided by 2 x minus a squared. And you might think this and guess a pattern, and you'd probably actually guess wrong. You might see these 2's and think, well, could I just keep going? F triple prime of a over 3x minus a cubed. And no, you can't. But that's because this number is actually something called a factorial. And 2 factorial is 2 times 1, whereas 3 factorial is 3 times 2 times 1. And so, you know, that stays the same, but 3 factorial is 6. Anyway, that doesn't matter. That's in case you go on to take 255, you'll see this. But okay, none of this matters. We just care about the quadratic. There it is. And we can plug in, look, we have all these numbers now. Cosine of 0 is 1, so that's going to go here. This was the derivative, which was 0, so that's gone. That whole term is gone. The second derivative was -1, so we're going to have minus a half x minus, and then what was a? It was 0, so that's a 0. In fact, that's just x squared. Okay, so what I'm going to do, I know my formula is really messy, but what it says is 1 over 2 x squared. That's my quadratic approximation. That's this scribbling here where I've plugged in f of a, I'm using a as 0, okay? So I've plugged in 1 is what that becomes. This whole term was 0. That's the fact that this is 0. This -1 is this -1, which is this number. I have to divide it by 2, and then I have to multiply by x squared. So anyway, that's my quadratic approximation, and I just want to plug in 0.01. Okay, that was, sorry, I had to do some typesetting. Anyway, so that's what's happened there. What is, q of, oh, so this is where I put that. 1 minus 1/2 x squared. There we go. There you go. Cool. All right, see you next time.